Hello everyone, today we'll talk about the solution to the problem binary tree postorder traversal, where we have to return the postorder traversal of a given binary tree. So of course a binary tree, we are given a root, and that root has some value, maybe some left child and some right child, and that left child, right child can be either nothing or another binary tree. And postorder traversal, in this case, would be just a list of values of nodes in the order in which that traversal goes. So a postorder traversal is one of the three main types, where in the postorder traversal you first traverse the left subtree, then the right subtree, then the root. And of course in pre-order you go root, left, right, and in order traversal you go left, root, right. And really the solution, the recursive solution, is just the definition of the postorder traversal. Our result will be a list of values, and at the end we'll return the list of values of our nodes. And now we just start at root with our auxiliary function, and that function does nothing if it's called on an empty subtree. Otherwise it creates and adds to the list the traversal of the left child, then it goes and creates the traversal of the right child, and at the end it appends the value of the root. This problem also asks us to create a solution that's not recursive but iterative. And one way of doing that, of rewriting that recursion to iteration, because really a recursive solution seems simple, but in this case where we do not have tail recursion, and in particular when we first start with a single node, then the number of nodes that we're visiting may grow, because we have those two recursive calls in the middle and then we do something at the end. When it's executed, it's typically executed by just remembering the calls on the stack, remembering the state at which we're in, and we have to, when rewriting it to an iterative solution, do something similar, but we can either do it mechanically, or we can think about the nature of the problem and try to come up with a different approach, with a simpler approach. So one way of doing that is to notice that when we visit a node, there are two things that we want, or essentially we want to visit a node two times. We want to visit a node the first time, in which case we want to add to our stack both the left and right children. And then we want to visit the node again, when both the left and right child have been processed, to append it to the result. So we can remember whether we're in the first phase or the second phase, along with the node on our stack that we're simulating a recursion of. So we start at root, and this false tells us if it's in the first phase or if the first phase was already processed. So it starts with false, which means that we still have to add its children to the stack. And now while there is anything on the stack, we take the thing from the top of the stack. So we just pop it. The stack is of course a list in our case, because a list allows us to add to the back and remove from the back in constant time. If this is an empty subtree, we don't have to do anything. If this boolean is true, that means we have already processed all the children, so the last thing that we have to do is just to append the value to the result, and nothing to do more. Otherwise, we have to add the children, and then we have to add the result to the result, the value of the current node. So we have to process the left child, process the right child, and of course then we'll have to process their children, so their children are not yet processed, we put false there. And at the end we have to take again our node. In this time we remember that it was already processed, its children were processed, so we just put true here for it to add its value to the stack. And since the stack goes from top down, the last thing that we add will be the first thing taken. So to mirror this situation in lines 7, 8, 9, first left, then right, then append, we have to first left, then right, then append, write it backwards. So we write append the value as first, then right, and then left. And at the end, we still have the list. That's our result, and we can return it. So this is one way of rewriting this recursive solution to an iterative solution that is pretty mechanical, in the sense that there is before and including the first step where we recurse, and then after we go back to the execution of our function after that recursions, well, those two recursions, which we treat as a single one. So we just remember which step we're in. If there were multiple recursive steps, we could remember that we're in step 0, step 1, step 2, and so on. So that is one way of approaching it.